So we're going to discuss the travelling salesperson problem today, and we're going to look at Hamiltonian cycles, nearest neighbour algorithm, lower bound algorithm, and then we're going to see if we can do the whole problem on a matrix. So first of all, we're going to discuss what is a Hamiltonian cycle and how that's going to help us solve these travelling salesperson problems. So simply, a Hamiltonian cycle is a cycle, which means it starts at one node and finishes at the same node, so it makes a cycle, and it has to visit every node in the network on the way. So, for example, I could start here, and if I tried to go up to this node, and then to this node, and then back to this node, I can't now get to this node without visiting a node I've already been to. But I could try and do it if I started here, went to this node, then up here, then round, then down here, and then finish back where I started. And that there is a Hamiltonian cycle. I visited every node and got back to where I started. A Hamiltonian path, something slightly different, is just a path that visits every node but doesn't get back to where you started. So a cycle is a cycle. So let's have a look at this nearest neighbour algorithm now. What the idea of the problem is, it's called the travelling salesperson problem, and the idea is somebody is at a certain town and wants to visit every other town in the network to sell their products, whatever it might be, and then get back to where they started. So it's the same idea as a Hamiltonian cycle really, except they want to do this travelling least distance possible. And usually the edges on the graph are weights which represent distances or times it takes to travel between the towns. So what we're going to be trying to do is trying to start at a certain place. Where should he start? Travel to every other node in the network and get back to where we started. Now, unlike some of the other algorithms that we're doing in D1, for this one we might not always get an exact answer for the optimal route. What we're actually going to get is an upper bound for the answer and a lower bound for the answer. And between this upper bound and lower bound, there is an optimal route. So what we're going to try and do is, first of all, we're going to use the nearest neighbour algorithm to find an upper bound, and we want to make that upper bound as low as possible. And then we're going to use another algorithm to find the lower bound, and we're going to try and make that lower bound as high as possible. And then the actual optimal answer will be between the two. So we're going to try and get to our optimal answer by closing the upper and lower bound and trying to close that gap up. Okay, so the nearest neighbour algorithm is an algorithm that is going to tell us the upper bound. And it does exactly what it says on the tin really. It's the nearest neighbour algorithm. So we're going to start at a particular vertex. So we're going to start at A. And then what we do is we go from A and we travel to the nearest neighbour. So we travel to the nearest vertex which is connected to A. So we're going to go A to B, because that's just 6. So A to B is 6. And then from B, I go to the nearest neighbour, but I don't go back to A. I'm going to go to the nearest one connected to B, which looks like it's going to be, I've got 13 to E, I've got 11 to D, so I think it's going to be 11 to D, so we're going to go B to D, and that's 11. And now I'm at D, I'm going to go to the closest to D that I haven't already been to, and that's going to be C. D to C is 7. And then from C I'm going to go to the closest vertex that I haven't been to yet, and that's just E. So I have to go to E, so C to E is 9. And now I'm at E. Since I've been to all the other vertices, I have to go directly back to A. So E to A is 9. Okay. And so if I was starting at A and applied this algorithm, I would have 6 add 11 is 17, add another 7 is 24, add 9 is 33, add another 9 is going to be 42. Okay. So the total for that nearest neighbour starting at A is 42. Okay, now, so we've got 42 if we started at A. What we have there is an upper bound. So let me put this down. An upper bound is a route which exists but may be improved on. An upper bound is a route which exists but may be improved on. So let's just talk about what that means. I've just done a route starting from A, and the route was A to B, B to D, D to C, C to E, and E to A. So what I have there is a route that exists, and I know that it exists because I've just done it. Okay, A to B, B to D, D to C, C to E, E to A is a route that exists. And we've got a total of 42, so it's a route that exists, but it might not be the best route. There might be a shorter route, so it's a route that exists, but may be improved upon. So at the moment, this value, 42, is the upper bound for the answer. Okay. Now if I was to do this nearest neighbour again, which I'm going to do in a second, starting from a different vertex, then this upper bound, 42, might come down. Next time I do it, it might come down, and then I've improved upon it. So at the moment, this is the best upper bound I have. 42 is the best upper bound. So you have to remember these definitions. An upper bound is a route which exists but may be improved upon. And then I'm going to add to this the best upper bound is the lowest upper bound. Okay, so at the moment the best I have is 42, and now I'm going to do the nearest neighbour algorithm again, and this time I'm going to start at B. Okay, so I start at B, and I'm looking for the closest place to B. The closest place to B is A, so I'm going to go B to A, which is 6. And then from A, I visit the next vertex, which is closest to A that I haven't been to. That's going to be A to D. And A to D is 7 away. Okay. And now I'm at D, I'm going to go to the closest place to D that I haven't already visited. So D to C, that's 7 as well. And now I'm at 7, I'm going to go to the nearest place to C that I haven't already visited, and that's going to be E. C to E is 9. And now I'm at E, I have to go back to A. So I've visited every vertex now. So E to A, oh sorry, E to B is where I started. So E to B, and that's, I've got to go straight there, so that's 13. And I'm going to add these up. I've got 6 add 7 is 13. Add 7 is 20, add 9 is 29, and then I'm going to add 30, and I get 42. So still, the best upper bound I have is 42. Okay. Again, it's a route that exists because I've done it, but it might not be the best route. I'll have to just keep going. Okay, so I'm going to do one more. This time we're going to start at C, I think. We'll start at C, and then we'll see if we can get that upper bound to come down. So this time start at C. And if I start at C, the closest place to C is D. So I'm going to go C to D, which was 7. And then closest place to D is A, D to A, that's 7. And now I'm at A. The closest place to A that I haven't visited is B, which is just 6. And now I'm at B. The only place I haven't been to is E, so it's going to be B to E 13. And now I'm at E. I have to go, I've visited every vertex now, so I have to go straight back to where I started, which was C. And E to C was 9. Okay, and we'll total these up. 7 add 7 is 14, add 6, that's 20, add 13 is going to be 33, add another 9, that's 42. Okay, so I've got 42 again. So still the best upper bound I have is 42. We'll do one more, I think. So this time I'll start at D. And D, the closest place to D is A or C, so let's do D to A, and that's 7. And then when I'm at A, I'll go A to B, which is 6. And now I'm at B, the closest place to B is D, but I've already been to D, so it's going to have to be B to C is 12. And now I'm at C, I have to go to E. C to E was 9. And now I'm at E, I have to go back to where I started, so that was E to D, and that's 10. Okay, so I've got 7, add 6 is 13, add 12, that's 25, and then I've got to add 9, which is going to be 34, and then I add 10, which is going to be 44. Now, out of all of the routes that I've done, we've got, starting at A, we got 42, starting at B we got 42, starting at C we got 42, and starting at D we got 44. These are all upper bounds for the route, but the best upper bound is the smallest, the lowest upper bound. So the best upper bound for us so far is 42. So if I want to start somewhere and visit every node and get back to where I started, the route is going to be 42, because I've shown that there is a route that is 42, or it's going to be lower than 42. Okay, so I've shown that there is a route that's 42, so there is a route that exists, and I know it exists because I've done it. There might be one lower. So we know that the optimal route X, whatever the best route is less than or equal to 42. Okay, we haven't found one better yet. And if you want to just keep doing the nearest neighbour algorithm, you can keep doing it starting at a different vertex each time, and you just pick the lowest of the upper bounds, and that's going to be the best one. So we're now going to talk about this lower bound algorithm, and the way this works is, firstly we're going to delete, or sometimes we say omit, a vertex, and we'll start by deleting A. And what you would want to do is draw out this network without A in it. So let me show you what I mean. So if I got rid of A, then there would be nothing to connect to A. So I'm going to draw out the network again. So I've got E here, B here, C and D. and they're still connected, and they're still connected, but there's no A node up here, so there's nothing to connect to A. I'm going to put the edges in again. So I've got 10, 9, there's no 7, there's a 7 here, 12, this one was 11, and straight across there is 13. And I'm going to put the A connection on its own over here. So this was A, and there were 4 edges coming off A, and they were 9, 7, 8, and 6. Okay. And I'm going to concentrate on this network here that hasn't got the A in. And what I'm going to do is I'm going to find a minimum spanning tree for this network here. So I'm going to find a way that I can connect up all the nodes just on this minimum spanning tree here. And to do that I can use Prim's or Kruskal's algorithm that you should know. So we're going to use Prim's, I think, yeah, we'll use Prim's. So I've deleted A, and then I'm going to find a minimum spanning tree for this network. So find a minimum spanning tree. Spanning tree for the network with the deleted vertex. Okay, so we're going to use Prim's algorithm, and let's say we start at E. So Prim's is the one where we start at a certain vertex. Start at E. It doesn't matter whether you use Prim's or Kruskal's, but we're going to use Prim's so we can see how we do it on the table later. So start at E. I'm going to go, closest place to E is E to C. So E to C is 9. And then from C, the closest place to C is D. C to D is 7. And from D, I have to get to B, and that's going to be 11. D to B is 11. It's a minimum spanning tree. There's 4 nodes. I've got 3 edges. I haven't made a loop. You've got to remember to do all that. And I've got 27. So the minimum spanning tree of this network here is 27. And the minimum spanning tree means that I can get from each node to every other node in that network. So I can get from E to B by going from E to C to D to B. So I've made a minimum spanning tree for this network. Let me just draw it on so you can see it. Okay. So everything in that little network there with the deleted vertex is traversable. I can get from E to B. Okay, they're all connected. And then what we do with the bit that we deleted, this A over here, with the connections from A's, this is sort of our route into this other network. Okay, so I'm just going to pick an edge that goes into here and an edge out. So I'm going to pick the smallest 2 edges from the bit I deleted. And so I'm going to add to this the smallest 2 edges that are connected to A, and that's 6 and 7. And that's going to give me a total of 27 plus 6 is 33 plus 7. Total is 40. Okay. So what I've done is I deleted a vertex, in this case A, drew out the network without that vertex and found a minimum spanning tree for it and found the length of the spanning tree that connects everything up. And then I added the 2 smallest edges that were connected to that vertex that I deleted. And that is the lower bound. So I now know that my best possible route, let's just put it like this. This is the lower bound. This is a lower bound. So I now know that my best possible route Well, we know it was less than or equal to 42, okay? And we know that because we did a route and it was less than, we did a route and it was 42, so the best route has got to be 42 or less. So now that's true. And I also know that this lower bound is 40, so the actual answer, the best possible route, is somewhere between 42 and 40, okay? And the opposite with the lower bound, the best lower bound is the highest lower bound, because we want the upper bound to be as low as possible and the lower bound to be as high as possible. So the best lower bound is the highest lower bound. And the reason we can't just say this is a route is this route might not exist. We're not always sure if this route exists. We know the other route exists because we actually did the route. However, on this one we've used a slightly different algorithm where we say this bit's connected and we will join up this bit here. That doesn't necessarily make a route. Okay, so we have the upper bound and we have a lower bound, and the actual answer is somewhere between the two. Sometimes the upper bound will be equal to the lower bound, and then you know that is the actual answer then. Okay, finally, we can do this whole problem on a table, okay, a matrix like this. And let me just show you how to do that. Let's first of all find an upper bound. And if you remember how we do this, we start at a vertex. Let's start at A. Okay. And all I have to do for this is just look down this A column here. So the matrix shows you how all the nodes are connected. And I just keep going to the nearest place. So the nearest place to A is C. So I do A to C, and that's 5. And now I'm at C. The nearest place to C is that I haven't already been to is B. So C to B is 7. And now I'm at B. The nearest place to B that I haven't already been to is D, which is just 4. So B to D is just 4. And now I'm at D. The nearest place to D that I haven't already been to is E. In fact, E is the only place I haven't been to, which is 11. And remember, from E, I go back to where I started, which is A. So E to A is just 3. And that gives me a total of, let's have a look, 5 add 7 is 12, add 4 is 16. That's going to be 27, this is 30. And so that's an upper bound. 30 is my upper bound. And if I started at B and got a lower value, that would be a lower upper bound, and that would be the upper bound I picked. But I'm not going to do that. I've done it at A, I have got an upper bound. Let's have a look at doing the lower bound algorithm. So that was the nearest neighbour algorithm. And let's remember how we went about doing that. So now we're going to find a lower bound. By deleting A. We'll use the same node again. It doesn't matter that they're both A. And let's see what we would do on the network. So we start by deleting A. Okay, so what we'll do is we'll just take A out of that there. Okay, this is how we did the algorithm before on the network. So we delete A, and then we do a minimum spanning tree on what's left. So we should know how to do a minimum spanning tree on the rest of this table. And we've got to use prims on a table. So let's start at B. And if we start at B, then if you remember how to do this, we put a little 1 above B, and I cross out B, and I look down the column of B and I pick the smallest one, okay? And it's B to D. Start at B, so B to D is 4. And since we went B to D, that means D is the second place I go to, and I cross this out. Okay, and then I look down both of these columns, and I pick the smallest one out of both these columns here, and that looks to me like, well, we picked 4 before, now I'm going to pick B to E 6, so I've got B to E 6 there. Okay, and here's the next place I go to, so I put a 3 there and I cross this out, and then I'm going to look through all 3 of these columns and pick the smallest, and it looks like it's going to be B to C 7. Okay, so I've got my minimum spanning tree. So B to C 7. So the minimum spanning tree gives me a total of 17. And then what did I do? Well, what I did was I added on the 2 smallest edges that came from A. And the 2 smallest edges that came from A, or come from A, I should say, are A to E and A to C. And that's 5 and 3. Okay, which gives me a total of 8. And then I add these together and I get a total of 25. So I've got an upper bound. So my best upper bound is 30. And my best lower bound is 25. And the actual real answer, I don't know what the best possible route is. All I know is that it's less than or equal to 30 and greater than 25. Okay. Again, I know that 30 was a route, but it could be improved upon. So an upper bound is a route that exists, but could be improved upon. I know it exists because I did it. I'm not too sure whether this one actually exists, so it just becomes a lower bound. And that's how we can do it on a table. And that is the travelling salesperson problem.